All right. Okay, welcome everyone to today's stream. I've got the great pleasure of introducing John DeBrota, and we're going to be discussing quantum Bayesianism. So a really interesting topic, and John's kind of like one of the experts in the world on this. So I'm looking forward to it.
Awesome. So should I share my screen?
Yes, let's go
Go
for it.
ahead.
Okay, great. Share. And then, um, all right. So I made a presentation. I'm delighted to be here. Thank you, James, for the invitation. I will be talking about cubism, otherwise known as quantum Bayesianism, and that is an interpretation and ongoing ontological project trying to understand reality, interpretation of quantum mechanics, in case that wasn't clear from quantum Bayesianism. And ontological project means basically we're trying to understand reality. So in that sense, it aligns with what the Wolfram Physics Project is trying to do. And I do believe that eventually an engagement between the Wolfram Project and Cubism will be mutually fruitful. But in order for anyone else to agree with me on that, you need to know something about Cubism. So today I'm going to talk about the why, the what, and the where. Why, basically the motivations, the initial questions that led to Cubism, what being what Cubism is, and where we're going roughly. So let's get started. Oops. Okay. So I'm working at the University of New Mexico in Albuquerque at the Center for Quantum Information and Control. This building, I don't know if you can see my cursor. I hope you can.
Yeah.
This building is, okay, great. This building is where we work. If you zoom in really closely to this window, you'll probably see me giving the lecture right now. And the Center for Quantum Information and Control obviously has a strong focus on quantum information. I am actually at the intersection of that with another field called quantum foundations. And quantum foundations, if you don't know, basically asks the question, what is it about reality that gives us quantum theory? And if you're not in this field, you may not realize the extreme lack of consensus there is to this kind of a question. It may seem like, well, quantum mechanics is well established. Surely everyone knows what the heck they're talking about. It's a little bit more subtle. And this is troubling if we want to make progress on fundamental physics, because unless we know what a theory is, well, how do we properly generalize it? We have to be very careful. There are some basic issues for about 100 years now. Quantum mechanics first appeared almost exactly 100 years ago now. Why are there two kinds of evolution? This is known as the measurement problem. Dynamics and measurement are two different ways that states can evolve. Are quantum states physically real? Is quantum theory non-local? This is something you hear a lot due to entanglement. Why, for instance, does classical mechanics usually work if the true description in some sense is quantum mechanical? And then, where do these pop science clickbait headlines come from where people talk about many worlds or spooky action at a distance or a particle that takes every path, et cetera, et cetera? And here's the warning before we get started from Alexander Pope that a little learning is a dangerous thing. I put this up just because quantum foundations is very contentious. Why do I say that? Well, basically, you learn quantum mechanics in school and you basically inherit a implicit interpretation of some sort. You get comfortable with that, you work on that, you then write a bunch of papers. And then someone comes along and sort of challenges your basic preconceptions about the theory. And that can feel a little threatening. So let's all try to be a little bit less judgmental and approach this with an open mind. And let's first start with what is not contentious, in fact, which is the quantum formalism itself. So the mathematical structure, or at least up to isomorphism, what are we talking about? And I'll explain this from the quantum information broadly side. So everything takes place in a complex Hilbert space of d dimensions. D could be infinity, it changes the situation, but fundamentally we're usually talking about finite dimensions in quantum information. We have vectors that we write as bras, as kets, and their conjugate transpose is bra. Inner product looks like bra-ket notation. This is all due to Dirac. People usually like to use this. Then a quantum state for some system is a linear operator on this Hilbert space, which is positive semi-definite and trace one. That's the full expression of what you have. Among these, the extreme points are known as pure states, which can be written as an outer product of two pure vectors here. And then,
Sorry, Dugan, there's background noise on your side. No problem.
is there a question? Okay. If we have more than one system, then we conjoin systems by taking the tensor product between them, and then quantum states on the joint system is a linear operator on the joint space. Measurement is a positive operator valued measure. What that means is it's a set of operators where the individual elements are called effects. Each of them is positive semi-definite, meaning the eigenvalues are non-negative, and they all sum together to make the identity. This together with the quantum state concept and gives us the idea of how we get measurement probabilities. And so this is the Born rule. It takes a state, it takes a measurement outcome, and it tells you the probability and how they fit together. That's fundamentally why we needed this to sum to 1 and why we needed this to be trace 1, so that probabilities are conserved and positive. And finally, states can change. So there are transformations. In general, these are completely positive maps. That just means that they're positive even when you act on a subsystem of something that could potentially be entangled. And they include things like unitary evolution, which most people who've learned about quantum mechanics are familiar with. So this is a very general setting, but it's isomorphic at least to all of the structure that anyone who's learned about quantum mechanics is familiar with. And this is not contentious at all. Everyone agrees so far. The real question is, what does this mean for reality? And there are two broad kinds of reaction. The first one I'll call the ontic reaction, which just says, well, basically the formalism is the reality. The mathematics captures structurally what's real. Or in other words, reality is in one-to-one correspondence with those mathematical terms in some sense. And this is very natural for a physicist because that's basically what we've had to deal with in the past. Feels very familiar from classical physics. And particularly, for instance, this motivates the so-called many worlds interpretation, which tries to just take the structure and say, okay, well, if that is physically real, what does that mean? And they say things like, well, okay, if you have a quantum state for a system and the whole universe is a system, well, then we can talk about the quantum state of the universe and just turn the mathematical crank, and that's what reality perhaps is. The other broad attitude is the so-called epistemic attitude. And this says that the theory is only indirectly about reality. In other words, the theory is about information or knowledge or belief packaged somehow in such a way that it's suitable for this world. And the mathematics then would be a convenient packaging for this purpose. So the Hilbert space formalism that I showed you before is very nice and economical and parsimonious, so to speak. But broadly speaking, the important part is that there is an informational component to this. And this is very different from most other physical theories, except perhaps statistical mechanics. But even then, there's a crucial difference that we'll get to in a second. And it turns out that in this side of things, there's no quick answer to what is real. Now, why do I say that? Well, let's first meet these three gentlemen who were champions of the epistemic view, Einstein, Podolsky, and Rosen. And Einstein, in particular, had just developed relativity like 15 years earlier. This is the 1930s, by the way. And he was very adamant about the fact that there should not be influences that happen faster than light. So this is actually Einstein's argument, not the three of them. The three of them famously wrote a paper together, but Einstein himself had this argument. Well, if states were real, i.e. ontic, then the choice of measurement at A for some two-part system will affect the real state at B when you make a measurement instantaneously, which violates locality. And this could be this can happen instantaneously if there were entanglement between the two systems. So Einstein concludes that quantum mechanics is correct, but not complete. And he says, well, it's a really nice statistical theory, just like statistical mechanics, but there should be an underlying story of other variables that interact locally and they're real, and that's the real story. And it's a good attempt. It sounds right. But then these three more gentlemen came along, and in particular, John Bell said, unfortunately, that's impossible. So Bell proved that basically there is no way to complete quantum mechanics in terms of a local so-called hidden variable model. the consequence is you have to reject either locality or reality, reality being that there's some sort of pre-existing thing that measurement simply reveals. And the fact that you have to reject one or the other of these is simply known as quantum non-locality, typically, which is a little misleading because it sort of bakes in that you should reject locality, but let's not worry about that. The point is, okay, well, crap. We can't have what Einstein wanted. We can't have what Einstein, Podolsky, and Rosen wanted. Turns out it's impossible to have local hidden variables. So thinking of quantum mechanics epistemically must be broken, right? Ontic is the only option. Well, turns out that's not quite true. We know that a state is not simply equivalent to a probability distribution over a true set of affairs, hidden variable, local ontic state kind of deal. However, there are powerful arguments that quantum theory is nonetheless at least partly of epistemic character. So, for instance, just to warm you up for this, the idea is like if it's ontic, well, measurement update, like Einstein was saying, is this bizarre instantaneous thing. But if it's epistemic, then updating is very analogous to just getting new information. So consider I had like two coins and I know they're perfectly correlated. They're either both heads or both tails. Send one to the other side of the universe. If I look at mine and I see that it's heads, well, I immediately, instantly know the other one's heads, but there was no action. That's just me updating my belief. And in that sense, no new physics is needed for that aspect of it. Things are a little bit more subtle in quantum mechanics, but broadly speaking, you can interpret measurement in a information updating way. And for getting a really, really strong advocacy for this view, I recommend the absolutely brilliant paper by Rob Spekkens from 2007, Evidence for the Epistemic View of Quantum States, a Toy Theory. So what Rob did was he constructed a very simple toy model, which is explicitly local and real, so not anything that would upset Einstein, and imposed on it a so-called epistemic restriction. In other words, a bound on how much information you can have about the true state. And when you do this as just from the outside imposition that feels classical or quasi-classical at best, you reproduce a whole bunch of the quantum phenomena or phenomena that people assume were sort of characteristic of quantum mechanics and didn't appear in a classical setting. So a whole lot of what makes quantum mechanics seemingly strange is actually just about your information. More specifically, or repeat it. Yep.
Do we have time to quickly discuss that little square with the things and what the toy model is?
I'm not going to discuss that. I'm just telling you that this exists, but you definitely should go read it. These are expressions of states for him in the toy model. I think this would be extremely interesting to people at Wolfram Institute. This is an extremely good paper, so I would read that. I don't even know how many people this is.
For the viewers.
Yeah, and everyone else. I mean, this is it's radicalized a lot of people, I think, towards the epistemic view. I should add the caveats though. So this is an explicitly local and real toy model where we impose the epistemic restriction that I just said. And this produces analogies of most so-called quantum phenomena. So you see basically the analogy of non-commutativity, interference, no cloning, entanglement monogamy, teleportation, dense coding. I'm not going to go into what any of these are here because that's sort of not the point. The point is just that all of those effects appear when you've done nothing more than say, okay, I can't know more than this amount. Okay, so that much is enough to get so-called quantum effects. Or in other words, those aren't really that quantum. Quantum mechanics and what makes it actually special is a little bit more subtle. And what we want ultimately is to isolate what is truly special and different, and not wait around in a theory that E.T. Janes down here called in part realities of nature, in part incomplete human information about nature. So ultimately then, even though the real is not going to be just like a variable that's pre-existing your measurement outcome, it will be something more subtle, unlike anything before perhaps. Even though that's the case, I believe that only the epistemic route can get us there. Okay, so that's sort of the why. And all of that's leading up to my next slide, where I give a sort of broad overview of what quantum Bayesianism or cubism is. Okay, so You can read about it on Wikipedia, and in Wikipedia, you can see a lot of good introductory references that you can read. Broadly speaking, it's at this point, I would say, one of the main interpretations of quantum mechanics. Adherence to it is perhaps lower than a lot of other interpretations so far, but perhaps that's because it's also one of the most radical. So why do I say that? Most, in fact, perhaps basically all other interpretations start by answering this question about what is it about reality that gives us quantum theory by asking the associated question, what are the basic objects of the world and how do they behave? And when you ask this question, you crash directly face first into the so-called measurement problem. Because as soon as you're talking about objects and their dynamics, then one has to immediately try to see measurement itself as a physical process as part of that dynamics. So that's hard. There's been a lot of attempts to do that. I don't think any have been considered sort of universally convincing, and it's a perennial problem. Cubism just says, well, what if measurement isn't a problem? What if measurement is actually the fundamental, most primitive thing? So we dissolve the measurement problem by just taking measurement to be fundamental, and then see how much of the rest of the situation you can get. So from an interpretation point of view, we take measurement to be fundamental, and then we give the rest of the theory a so-called decision theoretic interpretation, or essentially an informational interpretation, and see if we can extract from that ontological statements. So note that I am making a distinction between ontology and the interpretation. So the interpretation is just a step along the way. This is a contrast to other interpretations, which basically just start by positing an ontology from the beginning. We want to try to find that ontology by getting the interpretation right. And taking this sort of attitude ends up pointing us in a different kind of direction for the kind of reality that it seems to be implying than, say, is in the prevailing scientific culture. So for instance, action or measurement creates instead of reveals. It is actually building the world in a sense. Reality is perspectival, i.e., it doesn't admit a view from nowhere. Everything has to be always from some situated perspective in the world. Experience is more of a primary than a secondary concept, etc. Okay, so that's a very high-level overview. Let's look at some tenets of cubism, which appear in this paper by Chris Fuchs. I think I forgot to mention Chris Fuchs and Rudiger Schock coined the term back in 2009, 2010. So the interpretation is relatively young, although there's about 20 years prior to that of development that was motivating it. In any case, in this paper from a couple years ago, Fuchs laid out 8 tenets. I'll basically just read them to you, and then we will analyze a little bit of them going forward. First tenet, a quantum measurement is an agent's action upon its external world. A measurement outcome is the experience of the agent taking the action. And it's important when you say this that you understand a measurement device as a conceptual extension, or like a prosthetic limb of the agent. So the agent takes the action through the measurement device. It does not take the action on the measurement device, if that makes any sense. A quantum state is an agent's personal judgment rather than a part of the furniture of the world. Even unitary operators or completely positive transformations are personal judgments, so also those are. And then the quantum formalism as a whole is so-called normative rather than descriptive. And normative is about what should be or what you should do, rather than descriptive being saying what is. So we'll talk about that a little bit in the next slide. Even probability 1 assignments are judgments and thus metaphysically fallible. Why is that? Because the probability belongs to the agent using it. Even in subjective certainty, unperformed measurements do not have outcomes. And finally, quantum theory is a single user theory for each of us. Okay, so those are 8 tenets. Let's note some things. So again,
can I ask a quick question on that one?
Yeah, sure.
So to just double check something. So you mentioned the measurement device. I don't know if it's actually written explicitly here, but the measurement device, the agent performs the measurement through the measurement device, but not on the measurement device.
Yeah. So in order to, it's always essentially a binary in cubism. You always are thinking system and agent. We don't try to break it into a sort of trinary or Yeah, where there would be like system, device, and agent. You can talk that way, but then maybe it's more appropriate to say there's an agent and a system where the system is the device plus the original system. And
Yeah. So
yeah,
my question was just, do you need the measurement device at all? What if it's just the agent and the
you don't.
environment?
So
Yeah.
so fundamentally that means you don't need the measurement device, except that, of course, in our world, if I want to act on something like an electron, I need to enhance myself in some way such that what I do is I take an action on the electron. And the way to think about that is that the whatever device it is that I'm using to act on the electron is sort of a part of me for
Yeah.
that
Yeah.
for that purpose.
Yeah. Great. Okay.
So again, this is the interpretation. It's not the ontology. Our strategy is explicitly top down. So we are assuming the existence of things like agents, and the world out there, but this is something that agents in the world use. The individual objects like states, unitaries, transformations, Hamiltonians, everything, those are all relative to agents, but the overall structure itself is not. So the overall structure is objective or interpersonal or whatever the right adjective is here. That we don't violate. That's sort of about the world. But one person navigating the world and the state they use doesn't necessarily have to agree with the state someone else navigating the world uses. And so towards the ontology, towards the real, one thing you could say is one approach to that is to ask, what is it about this world that could compel an agent to rationally adopt this reasoning structure? So the quantum mechanics itself is a reasoning structure in cubism. So that's sort of the question cubism asks, or one of the questions cubism asks, instead of what are the basic objects, how do they evolve? So quite a lot of the previous tenets were powered by our understanding of probability, and they're going to seem odd until you're sort of on the same page, or at least willing to entertain the same page as we are about probability. So let's take a brief detour into probability theory. So what is probability? So one attitude, and the prevailing attitude probably overall, is that a probability is a feature of the world, meaning a frequency that an event will happen, or perhaps some natural objective chance, likelihood, propensity. These are terms that people throw around. The other attitude, which is broadly associated with the so-called Bayesianism, is that a probability is a degree of belief, i.e., a quantification of your willingness to take an action. So this is on the left is the one we're used to in physics, because, after all, we like to think about things as being objective and out there. And the degree of belief situation is sort of obvious for like a weather forecast. What's the probability it's going to rain today? Well, I don't give that a frequentist interpretation. But what if probabilities always mean this? Even the ones that we see in physics, even the ones we see in quantum mechanics. And cubism essentially begins when we swallow this pill. So in particular, we're swallowing the subjective Bayesian decision theory pill, and probability theory is part of that. And in there's many ways to formulate this, but the idea is that probability theory operationally arises out of coherent preference in decision making. This is due to Bruno De Finetti, Ramsey, Savage in the last 100 years or so. It's illustrated quite nicely by the so-called Dutch book story. Basically, what you do is you say, okay, let's quantify your willingness to act in terms of gambling. So your willingness to act with a price that you would be willing to buy or sell equally, so where you're ambivalent, a ticket that's worth $1 if an event A occurs and $0 if it doesn't. So how willing are you to buy that ticket or sell that ticket? So what price would you assign to that? And then the key is you never assign a set of prices for a whole bunch of different things that you would consider fair, such that some combination of buying or selling them would lead you to a sure loss no matter what happened. So very simple example of how you could get to a sure loss is if you said, okay, a ticket that will pay $1 if it rains today, I'd pay or sell that for 60 cents. And if you also consider a ticket that says, what's the price you would pay for a ticket if it doesn't rain today? And you say, okay, I think a fair price for that is 50 cents. Well, that means someone could sell you both tickets. It will rain and it won't rain. You would pay $1.10, And no matter what happens, you're losing at least 10 cents, okay? That is irrational from at least some certain points of view. And at the end of the day, what happens is that the standard probabilistic rules for probability theory arise simply from consistency among simultaneous gambling commitments. All this to say, punchline, probability theory comes from internally self-consistent reasoning. It doesn't come from the world. Okay. Points of emphasis. Agency, of course, is primitive because this is just something someone uses. We're not, probability theory or decision theory doesn't tell you how to build a human or any other agent. And then, of course, since this is for each person to use one at a time, no in principle consistency between agents. Another thing to note is that it's about now. It's about what your beliefs are now and whether they're coherent, so-called now. It does not fix how beliefs change. So, for instance, Bayesian conditioning, updating with Bayes' rule, is something that you can talk about and talk about when you would believe or expect to do so, but it is not mandatory from the subjective Bayesian point of view. There's other kinds of update you could have, or you could just start all over if you have different beliefs. Another thing to note is that no probability is right or wrong in isolation. Those are scare quotes because they basically don't mean anything anymore. The point of probability theory is about detecting inconsistencies. It's not about resolving them. So if you detect an inconsistency, you just need to go back to the drawing board. It doesn't tell you what the right probability is. Another point of emphasis is that probabilities 0 and 1 are probabilities of exactly the same character as any other. They happen to be the extreme cases, but they don't have a different kind of ontological meaning. Certainty is a belief, it's not a fact. And then finally, a pet peeve of mine, probability theory itself is not classical in the sense of classical physics. Again, we just saw that it comes from internally consistent reasoning. And so an agent should adopt it irrespective of the world she inhabits. Quantum theory does not refute any aspect of probability theory itself, for instance. However, the character of the world may suggest additional probabilistic constraints. So quantum mechanics, indeed, in cubism, is thought of as additional probabilistic constraints on traditional Bayesian probability theory. So let's go back to our tenets and let's consider them. These ones that I've highlighted in orange are all just clearly about decision making. We have action upon the world and the consequence. Okay, so action and consequence, that's about decision theory. It's single user, of course, like a decision theory would be. And then the normative is about, okay, it's giving us advice about the action that we can take. Typically in subjective Bayesian decision theory, the action that you would be recommended is one that maximizes your expected utility. We could talk about different foundations for decision theory, and perhaps there would be slightly different variants of cubism if you did so, but that's not the point of this talk. The rest of these are directly about probability, which, as we saw, is a part of decision theory. And in particular, you can see that a quantum state is an agent's personal judgment. That comes from the fact that a quantum state is actually nothing more than a probability distribution. It's a probability distribution for a so-called informationally complete measurement, but it's simply a probability distribution. Similarly, unitary operators transformations can be understood as conditional probability distributions for an informationally complete measurement. And so if we're serious about subjective Bayesianism, and we think that probabilities are not part of the world, and we understand probabilities in terms of personal judgments and willingness to gamble, that just ports directly over into what we understand about quantum theory and quantum states and quantum operations. So explaining to you informationally complete measurements and how all of that breaks down would be another talk. Maybe I can give that some later time. But for now, I just want you to understand that basically, if you consistently adhere to subjective Bayesianism, you basically get cubism once you really cross all your T's and dot all your I's. And I believe that subjective Bayesianism is the strongest foundation for probability, but I should note that debates rage in the philosophy of probability. It's been going on for much longer because we've had a probability theory for much longer. And that would be another talk to address those. Another sort of reaction would be, did we really have to go this far? And I have a few comments on that. So first of all, it was consistency more than preference that took us here. But perhaps more than that, and although I won't dwell on it, in my experience, other interpretations, even if they're not outright inconsistent, will sort of end up endorsing things that, from my perspective, seem even worse or more upsetting. Of course, there's a personal preference aspect of this about what it is you consider going too far in one way or the other. And some people might consider cubism to be a pathology. But even our critics agree that we are consistent. And so I would say this is something that one should look into. And in particular, because we go so far, perhaps it's a very fruitful place to learn more from. So what if minor deviations from a sort of classical mentality or a pre-quantum mentality don't cut it? If we aren't willing to go far enough, we might not be able to see or learn the actual deepest kind of thing. Okay, so let's regroup and consider, let's go back to quantum mechanics and consider something else that's sort of essential to talking about quantum foundations, i.e. a measurement problem. And let me sort of recap or even introduce for the first time the usual attitude that one finds. So you encounter quantum theory. It's at least momentarily disconcerting. The theory seems to rope in an observer. There's two fundamental kinds of state change. And if the theory is irreducible, as Bell basically proved, then can we really be detached? Like, is there a us and an out there, a subject and object that are completely separate things? You know, I can always have memes in my talks, and we have the physicists reaching for the objectivity, but physics itself is pulling them back. The usual attitude is to double down. So you say, okay, I don't care. Quantum theory, you know, it's weird, but the theory still mirrors reality. Let's just say measurement is an illusion too. And the real is only visible from the outside, so to speak, outside of the universe, from nowhere. Nowhere, of course, being a very specific situated where, but we're not going to worry about that. And we're going to think about this in terms of the paradigmatic paradox, the Wigner's friend paradox, okay, which I will now introduce. So Wigner's friend, here's the friend named F. She has a system S in front of her, and she's going to take an action on it. She's going to measure it. All of this is taking place in some sort of a lab, which is obviously a rounded square. Outside the lab, we have Wigner, or W. And the friend models her action in terms of a quantum state for the system and a measurement on the system. She has some probabilities from the Born rule. When she gets an outcome, she updates to some quantum state for the system. Great. Wigner, on the outside, models the entire lab as some transformation. In general, it would be a completely positive map. And the friend makes a measurement, gets an outcome, has an experience. Wigner is not making a measurement, he's just modeling. So there's no measurement for him, no experience for him. Let's write it in a more provocative form for a very specific case. So let's say the friend initially has a superposition state, and this is a two-level system, superposition of up and down. And she's going to just measure in that basis, up and down basis. So she's going to project. And when she gets an outcome, she either updates to the up state or the down state. Meanwhile, Wigner outside initially describes the whole system as a big pure state. He has the system in one state and a tensor product with a so-called ready state of the friend and the lab. So then he models the whole thing with a joint unitary. So the whole joint system and friend composite evolves unitarily, and the whole measurement situation is then modeled by him as going to a entangled state, 2 up plus 2 down. This is one of the Bell states, if you're familiar with that terminology. Okay, so the friend got an outcome, and the friend updated to one state. Wigner did not get an outcome. His quantum state situation is different. The question is, who's right? Okay, so we have two different descriptions. They both use quantum mechanics correctly, so it seems, but they have different answers. And also one of them got an experience and the other didn't. What's going on? So typical responses, I will call one of them zoom out. Basically, you just take God's eye view. And basically who's right is answered by Wigner, or even better, God is right. Because measurement itself is an illusion from within a universal, unitarily evolving wave function. You know, no one really gets an outcome. Everything that happens in the world is actually just the unitary evolution of the universal wave function for the entire universe. Another reaction that's sort of a special case, or essentially along the same lines as the previous one, I call decoherence. So the idea here is that for anything like an agent, noise will dominate. And basically the environment around the agent and the system will effectively measure. And you put measure in scare quotes there because you have to deviate from a very principled stance about what measurement means in order to make this claim. But in any case, this kind of an attitude is developed by Wojciech and a bunch of other people. The idea would be that, okay, Wigner's actually wrong in the previous discussion because what he should do is access the information in the environment, and then he'd be able to sort of figure out what the proper decohered state is instead of his entangled state. A third attitude or reaction is, okay, actually, we can't solve the measurement problem until we find new physics. So you need to change quantum mechanics. One way to do that would be to say, okay, measurement is actually some kind of stochastic process, a spontaneous collapse, for instance. And we just haven't been able to detect new physics yet to figure out because it happens so quickly. But indeed, there are real collapses. The quantum state is the real thing, and it's just collapsing at stochastic intervals. A final reaction is I call loss of agency, which basically says that Wigner is right because the friend basically isn't a person anymore in this kind of a situation. The experiment steers her. Wigner could even undo her outcome with a further unitary evolution. And Wigner himself actually proposed basically this solution. Also, Scott Aronson wrote that it's really hard to think when someone hadamards your brain at some point in the past. So that kind of a reaction also has some support. So what are Cubism's replies to these kinds of solutions? So first of all, in this paper from 2024, I'll have references at the end. We address zoom out and decoherence by basically saying, we don't take dynamics as primitive, we take measurement as primitive. And in fact, we can derive dynamics from consistent reasoning about measurement. So that was actually a pretty nice advance in Cubism. I definitely recommend you all read this paper. But basically, at the end of the day, you don't need to invoke anything like a record in the environment. And it becomes more and more perverse from a Cubist point of view to just zoom out farther and farther. Because if quantum states are your degrees of belief, the more you zoom out, the in fact more highly rarefied kind of belief you would need to have. Another reaction is that we don't have any need to modify because the central move of Cubism was that measurement was fundamental and primitive. So I certainly don't need to talk about any kind of stochastic process that tells me what measurement is. And then finally, while the measurement or the situation may indeed imply some sort of loss of agency, there weren't any physical details in this really abstract thought experiment. So it's sort of missing the point to say that. Without any details, nothing necessarily implies loss of agency. And an important thing to note is that this is about different agents. So my strong beliefs, even if I have certainty about them, don't have physical hold over you. So just because I'm certain you're going to do something, that isn't forcing you to do it. Certainty doesn't let you cut out the subject. Another way to say that, just like it is true with probabilities, it doesn't feel like anything to be in someone else's wave function. So more broadly, Cubism basically says, well, what if the question is wrong? Who is right? What if that's not the right thing to ask? Basically, this is coming from a reflex to, so the usual question is coming from the reflex to assume the existence of objective third-person standpoint, which grounds the experience of our outcomes. And I think the fear is, well, I don't think, I know the fear is that without this fundamentally Cartesian move, understanding reality is impossible. But Cubism basically says this might be what's exactly holding us back. And essentially it nudges us towards a more interior view from individual agents, a perspectival view. The idea would be that experience is in some sense born in the interface of agent and world, and in some ways goes towards producing or the co-emergence of what we mean by agent and what we mean by world. Action or measurement or something to do with this spark that I put here is the more primitive and important thing we should be focusing on and where we should be looking for an ontology. Experience is not a property of either one in isolation. So so far as the Wigner's friend thought experiment goes, in a paper from 2020, Fuchs-Schock and I basically showed that although there are further questions you might want to ask, the spirit of the paradox is resolved if you simply treat everyone on equal footing with respect to their individual uses of quantum theory. So treat all agents symmetrically. So A, in cubism, the quantum formalism is only used by agents who stand within the world. There's no God's eye view. So this was meant to mean like we're viewing it from outside. In B, to make predictions, Wigner treats his friend, the particle, and the laboratory surrounding her, all shaded in green, as a physical system external to himself. So all of this is external to Wigner. So he uses quantum theory to treat that. There's no problem, really, if we then just simply say, well, the friend must reciprocally treat Wigner, the particle, and her surrounding laboratory, all shaded in green, as a physical system external to herself. Of course, they could end up with different predictions, but that's generically something that can happen in decision theory or in probability theory because different people are in different situated informational, contexts. Okay, so let's sort of recap. Cubism is about action. Quantum mechanics is about action. Measurement gives an agent an experience and the world novelty. And then we look for ontology at the interface, sort of the spark. The other guys, they start with an ontology. Reality is some kind of dynamics, maybe an evolving state. And then what you need to do is you basically need to understand how measurement, agency, all the familiar things of the world somehow emerge. And I illustrate this with God's immaculate wristwatch. There's a sigh of the universe on it, and it just evolves with the Hamiltonian. And we got the sun and the moon and the stars and everything. If you're cubism, because we're talking about measurement, really the question is, well, we need to be able to derive dynamics. The other guys need to derive measurement. In fact, we did derive measurement, as I told you, dynamics in this previous paper. So again, I encourage you to check that out. Measurement is the fundamental thing. That's sort of the driving philosophy here, and all the rest follows from consistency. Okay, so that's sort of what cubism is in the time that I have. Let's briefly talk about where it's going. And to know where you want to go, you need to know who your friends are along the way. And I should again note that it was mostly consistency with physics concerns that brought us here. But there are actually philosophies which have said similar things, almost entirely without any reference to quantum mechanics, interestingly enough, but it's interesting to note. It's just also important to realize that philosophy of physics, so to speak, is traditionally in the so-called analytic tradition. But this basically has little in common with what cubism ends up saying. So actually, the philosophies that we have more in common with are often called continental philosophies or non-analytic, sometimes postmodern. There's a whole lot of different genres. It's like music. It's very crazy. But I can list for you some subtitles of philosophies. So for instance, pragmatism, phenomenology, existentialism, enactivism, all of these say a lot of broadly similar things because they have a very strong emphasis of being in the world. Some particular philosophers that overlap very considerably, and some of whom actually did influence cubism, like for instance, William James, are James, Dewey, Bergson, Husserl, Merleau-Ponty, Sartre, Whitehead, Heidegger, Rorty, Schiller, Dreyfus. There's a whole lot of people, and basically an aspect of future work, a philosophical side of things, is to engage further with these to understand if, granted, they came to some similar concerns without quantum mechanics. That probably means that they have some things that we could use and then bring in with quantum mechanics to go further. For me, the biggest open question is about what an agent in a world is. It's sort of obvious that that's the big open question because we're top down. It's fine to interpret the way we have, and it's also fine to say, well, maybe we can postulate things about the world that would make an agent rationally adopt this kind of a reasoning structure. But if we really want to get into how agent and world co-emerge, that's what we need to study. And there are some leads for this. Eventually, maybe that could be another talk. Enactivism in particular, for me, I'm taking as a very suggestive starting point. And in enactivism, there are some connections to second order cybernetics. So finally, I'm just going to flash this on the screen. Some overlaps with the Wolfram model, which I'm still reading about. So this is all very preliminary, but these are sort of the vibes that I'm getting. Cubism and Wolfram model both consider the epistemics of an observer and their informational situation to be important. They are both very focused on discrete structures. I didn't really emphasize that, but that's true in Cubism as well. Through inactivism, there's this association with second order cybernetics. Recently read a paper from the Wolfram Institute that talked about how the Wolfram model in some sense is very naturally aligned with that as well for understanding what agents are. And finally, with this interior view that Cubism is promoting, there are arguments that the physics itself should be understood through a sort of mathematically constructive lens or intuitionist mathematics kind of lens. I didn't develop that at all here either. That could be a topic perhaps for later. But I saw similar commitments and things being stated by people from the Wolfram Institute. Some non-overlaps so far. The Wolfram model is more ontic in its treatment of quantum mechanics, so far as I can tell. It appears to me that analogies are being drawn for quantum mechanics right at the level of, oh, well, we have like a branching and multi-computation, and so that's sort of like superposition or entanglement. From a qubist perspective, those kinds of things shouldn't, or it's the real quantum mechanics is probably not going to be that low. You have to go to a much higher level where you already have an agent, and then you see quantum mechanics as something that the agent uses. So there will be some sort of back and forth on that point, I think. In general, Cubism is top down. Wolfram model is explicitly bottom up. We're just simply trying in the Wolfram model, you simply try to postulate a universe of computation or multi-computation and see what you can find in it. That's not necessarily bad because maybe we can meet in the middle. And also there seems to be, it's unclear, at least in the Wolfram model to me, whether the outside view is necessarily a coherent attitude to take. It seems that people want to talk that way. It probably is not an issue to talk that way, but it also might be irrelevant. From a qubist point of view, sort of the situated perspective is all that really ever matters. So with that, that's all I prepared. I guess I went a pretty good amount of time. There's my email if you want to reach out to me, and I'll leave these references up. Maybe I should also leave, I don't know, I'll leave the references up so that you can go check out those papers and I can take any questions you have. Let me make you guys not invisible. How do I do that? Oh, there we go.
That was great, John. I really appreciate that. Sorry, my connection might be a bit bad now, but I was interested in the potential implications for the connection to the anthropic principle if you take this approach.
Yeah, I haven't thought much about it because, like, I don't know what the force of the argument should be. Like, what we can do is we can just study what we have, and I see that, this is the theory that we have, and the theory is used by agents, but I don't know if we should argue against other universes just because we have this one and that kind of a perspective. So I probably shouldn't say anything more about the anthropic principle because I'm not 100% sure what it's trying to accomplish.
Sure. I think my thinking just is if you take this approach you've described, I would guess the anthropic principle would then imply that whatever the agent's beliefs are, it is creating the universe through those beliefs and then taking like the highest probability to them. But that's like a philosophical idea, I guess.
Well, I will say that this attitude, or a qubist attitude, is much less in favor of a sort of the universe is already out there. It's more along the lines of the universe is now and the Big Bang is here, like John Wheeler would have said. Things are being created at all times, and you need a perspective to talk about anything. So indeed, our sort of freely chosen actions do shape the universe.
Very cool. Okay, that was just my question. I'm sure Nick has got some stuff as well.
Yeah.
Oh yeah. Well, I'm trying to come up with a good question, like formulate the whole problem that they have, because it's like isn't it worrying that the whole non-constructivist approach, what with epistemic like knowledge updating instead of an actual ontological thing updating and trying to derive it somehow? It's like all of this, because I'm definitely like on the side of modify reply, right? It's like you have to like reformulate it and make it more constructive,
I
because
see.
otherwise, yeah, otherwise like cubism formalism makes it like basically like in math you have non-constructivism. You just like
Yeah. So I first of all, I think, although it hasn't really engaged yet, I'm planning to engage with constructive mathematics, and I think they are. I'm sort of working on it with a mathematician right now, actually. But cubism and constructivism, I think, are sort of natural conceptual brothers in that sense. Although there are some ways in which there might be some issues or things that we need to work on to fix, because, like, for instance, it might be that subjective Bayesianism is very non-constructive, and it's unclear to me how to deal with that currently. But yeah, so first of all, I do like constructive modes, but I don't think of thought, but I don't think that a constructive attitude necessarily implies that the way to talk about this for sure is in terms of like a different a modification to the formalism itself. Because from my perspective, the formalism itself is arising at a very high level of consideration once you already have agents who have essentially carved out for themselves a niche or a world. And it's applicable in that world where there are objects for them that are not necessarily the fundamental objects of the universe, if you even want to talk about those. And so I don't think that you necessarily are committed to the modify approach just because you're taking a sort of broadly constructive attitude.
Yeah. Well, in a way, it's like there's multiple formalisms, even mathematically, you can
Yeah.
formulate theorem differently. So in a way, I can see this like a relationship of cubism just like a mathematical reformulation, right? Plus some ontology, but it doesn't like add anything constructive to the picture of the quantum.
Oh,
I
see.
said the dynamics, like you said, we have to derive the dynamics. So it
Yeah.
doesn't due to dynamics.
Yeah.
But I agree that there's some benefit to actually have like
so
mathematical
yeah. So this would be the kind of place where there would be tension, but with, I think, possibly productive tension between like cubism and the sort of the more computational approach that it looks like the Wolfram Physics project is pursuing. Because that's like building in dynamics, whereas we are talking about just measurement, and it's sort of like, okay, it's top down, agents are free to make choices and everything, and we get dynamics in terms of reasoning consistently. And so that is still not sort of a fundamental, it doesn't seem to need to be a fundamental primitive part of the universe. And if that's the case, then that's suggestive, I think. Nevertheless, it could be compatible with a fundamental dynamics. You know, there's nothing that rules that out. And so, yeah, I'd just be interested to see how all of these things can fit together.
Yeah.
I think that's
so,
go ahead, Brian.
I'm sorry. Yeah, so I just wanted to get your view on this zooming out idea, and in connection to quantum information. Do you think maybe is there a connection? Is there a way that maybe there is the information loss when you do like a zooming out? So I just want to get your view on that.
So I think typically when people talk about zooming out, what they have in mind is you're zooming out, but also becoming like infinitely more powerful at the same time, in some sense. So you zoom out, but you actually are not losing anything. You're only adding. So they say, okay, well, if I take a big enough perspective and I'm really a god, so I can keep track of everything. I zoom out enough, then everything is a unitary evolution. And I can talk about your measurement as a blip in the wave function that is just unitarily evolving. and your experience of this outcome is a sort of feature of the dynamics of the wave function. And so everything is sort of an epiphenomenon from a big enough perspective. That's the mentality that's motivating this. My attitude is that it's sort of, I think the biggest issue is that it's sort of irrelevant because we are not in that situation. I don't zoom out and I can't deal with that kind of like I don't have those fine scale beliefs. If I zoomed out personally, if I zoomed out, things would get worse. I would lose information, as you say. So you know, it's sort of like a religious commitment to just say, okay, well, you know, we don't know what is going on right now, but if we zoomed out far enough, everything would be unitary, and we can relax because that's the fundamental ontology.
So like there's a connection to power. You have to like have the power to view everything.
It's a very non like agent-based attitude because it's immediately assuming that it's valid to talk about this view from nowhere and also a view essentially from an omniscient, omnipotent perspective. Like you need to be like Laplace's demon in the sky, also not in the universe, keeping track of everything. And that can be, well, potentially that's a valid point of view, but I'm not attracted to it.
Okay.
I very much like how the agents that are being talked about in the physics project would have to be someone that is, you know, finite and situated and has finite computational power, etc. Because that's actually what we are. That's how we act. And so the reason I find like a similarity between that and cubism is because cubism is saying, well, look, all of this is always for an agent, and so any limitations on the agent are, you know, that's part of the use of that's part of the physics as well, in the sense that I don't imagine I can always zoom out indefinitely to a super agent. I just say, okay, well, I am what I am, and I use quantum mechanics to manage my expectations for the consequences of my actions. You use it to manage the consequences of your actions, et cetera, et cetera.
So an agent is, in this view, embedded in the universe?
Yeah, I mean, the agent is part of the universe, yeah. And we believe there's one universe.
And the one universe has like a single state, and it's just each agent is getting a different reading out of that.
So we're refraining from postulating the universe as a state, so to speak. That's sort of the issue. We're taking like the agent and their world and the things in it, like my coffee mug and everything. It's top down. So those are already there for me. If I then want to use quantum mechanics, all it does is add to my world. So if I also encounter in my world an optical table with beam splitters and everything, then I can use the quantum formalism to enrich my ability to account for the consequences of my actions. So in that sense, it's completely top down, completely the opposite of a Wolfram physics type approach, which is completely bottom up. Nevertheless, I'm interested in sort of what's at the bottom, right? So we need to kind of reverse engineer. You guys need to forward engineer, and you know, potentially there's some meeting in the middle. Maybe we'll just miss each other, but it's a general strategy to be top down instead of bottom up. Probably the main thing that distinguishes us from the rest of physics, because physics is traditionally bottom up, but potentially if you immediately start by trying to postulate an ontology, well, there's just too many options. You're going to miss it. You know, we need to start with what we actually know, not try to derive what we know at the end of a long reasoning chain.
So, you know, how dependent is cubism on, or how dependent is this updating state of the universe dependent upon observers? or agents, I
Uh,
guess.
Yeah, so each individual agent will have a state. They take an action, they get an outcome. On the basis of that outcome, they'll probably update their state to help them account for future actions. That state is not sort of a real part of the world. And your state is not a real part of the world either. What matters is your actions, your consequences, and you know, insofar as we live in the same world, things you do, I expect will affect me. Things I do, I expect will affect you. And yeah, it's sort of from a plurality of perspectives that we try to zoom in on identifying individual characteristics of the universe at the end of the day. That would be the hope.
So is it correct to say like agents, which are basically measurement devices, right? In our case, that
Mhm.
In the process of this updating of their beliefs is basically doing some inference. So that's where the most of the Bayesian formula is coming from, right?
Mhm.
And
Mhm.
also when you also zoom out, you can then also have to incorporate this loss of information when the measurement, the traditional type of measurement happens. So in addition to this inference that the agent is doing, there's also some, in order to make a parallel to usual like projective measurements, which
Mhm.
has to incorporate also the information loss,
Mhm.
right?
Mhm.
From the zoom out. Or is it like
I see. Okay. Yeah. I mean, that's sort of how it's that's the way people talk and how it's described in like decoherence descriptions. If you zoom out enough, then you would say, okay, well, we can talk about a unitary evolution of the system and its environment. Some of the environment is sort of a measurement device. Some of the environment might be other, like maybe a bath of oscillators, stuff like that.
Mhm.
And if you one way to treat that is there's no information loss if you zoom out far enough, because it's all just in a big enough wave function. But from the situated perspective, there could be things like photon loss, et cetera, depending on what it is you're modeling.
Yeah, basically like from the cubism perspective, decoherence is just like a marginalization of the probability distribution.
Right. So yeah, decoherence and dynamics in general are more about what you think you would be indifferent to. So like, maybe I don't want to get into this too much here, but you can see dynamics and decoherence in terms of your consistency for your beliefs now and my beliefs at a later time. So just the fact that I expect that if I did something of a particular character in between, I think that wouldn't make a difference. If I thought that, then my state just is automatically decohered.
Yeah.
You can read about that in this paper.
Yeah, I would do. I was just imagining like this in this kind of formulation. You assume like there's a measurement device and the system when they get coupled together, your belief basically becomes like also this coupled system. So the distribution itself becomes like across the system. So in a way, the system becomes aware of itself, right? So you have a belief, right? And then it gets marginalized. So that's where the loss of information and decoherence happens, because it's like.
I see.
Yeah, because
I
your agent.
hadn't thought about it that way. Maybe you should maybe you should write to me this. I'll see to what extent I agree. But I think I don't know. I don't know what to say to that at the moment.
Okay.
Yeah.
You mentioned in your last slide that cubism is somehow discrete. Can you elaborate on that?
Yeah. So just typically what we've looked at in particular in terms of rewriting quantum states in terms of probabilities, we've worked in a finite dimensional setting. I think another good motivation for that is that at the end of the day, an agent has finite capabilities. Although on the other hand, in some ways, talking about continuous variable settings and infinite dimensional things is actually simpler than talking about really large discrete settings. So there's a give and take. But one thing that we've looked at in particular is information, like the landscape of informationally complete measurements. That's something you can study. That's something I studied in my PhD. With one of those, you can construct a probabilistic representation of finite dimensional quantum theory. And basically, long story short, there's a very nice kind of informationally complete measurement called a symmetric informationally complete measurement. And they satisfy several very nice optimality kinds of criteria in the sphere of quantum information theory. And their use for sort of expressing the probabilistic form of quantum theory as different from classical theory has motivated some of us to think that potentially they're one of the most important structures about quantum theory, and therefore one of the things that sort of tells us more about reality than other things in the theory do. Like someone's in particular quantum state doesn't tell you much about reality, but the fact that you have this particular structure that's isomorphic to the Hilbert space stuff I talked about before may be directly related to SIC POVMs, which is what they're called, in some intimate way. So I noticed like a paper by a few, at least one of you, Nick, the quantum potato chip. Yeah, and in that paper, SIC POVMs appear. So I think it's just a discrete structure that may be of particular importance to what quantum theory is. And I'm just sympathetic to that broadly. And so, yeah, that's sort of the connection.
Well, do you have like any intuition about the SIC POVM in higher dimensions? Because it's like in qubit case, it's obvious how symmetric it is, right? But there you just what the symmetric means, and
almost nobody has an intuition for that. So I can tell you, actually, I have some bonus slides about that. Oh, look at that, it's overlapping. I could just say, like, to produce probabilities for any other measurement, wow, this is annoying. The probability for a so-called reference measurement needs to contain all the information of the state. An informationally complete measurement can do that. All you need is for the POVM, positive operator valued measure, to span the operator space. And the dimension is d squared, so you need that many effects. And yeah, going on. So for example, in dimension 2, you need a 4 outcome measurement. And that's what Nick was talking about. The SIC POVM, for instance, this is actually the SIC POVM. It's just in the block sphere, it's just points proportional to points of a regular tetrahedron. In dimension 3, you would need 9. This is a very bizarre looking one. It's not a SIC. But the point of a SIC is that you have equiangular lines. So the tetrahedron, the points of that are proportional to equiangular lines in a complex dimensional space. Angle here just being a generalization from the inner product. And it's a very interesting and open problem whether in every finite dimensional Hilbert space, can you find a set of d squared of these? Now it's known that if they're the biggest kind of equiangular set that could exist would be d squared. You can prove relatively simply, although I don't remember it off the top of my head, that there can't be more than d squared. And it's also an intersection with the problem of the so-called 2 design, which gives you a finite set or a discrete set of points that approximate up to second order polynomials, averaging over quantum state space. It's the smallest that those can be. So minimal 2 design, maximal equiangular set are SIC POVMs. Very interesting open problem. And it's actually related to Hilbert's 12th problem, turns out, which is a problem in number theory. It's unknown exactly whether SICs exist, but it seems very likely that they do. And for other reasons that I already talked about, like the fact that I think it's very important for the foundations of quantum mechanics and therefore for reality, this very deep mathematical structure, discrete structure, maybe is of interest.
So you mentioned for dimension 2, so looking at 2 qubits and the
No, not 2 qubits.
Oh.
One qubit, 2-dimensional. So a single qubit.
Okay. And you were mentioning how that can take on
Yeah,
4
so
different values.
Yeah,
on the
well,
block
so
sphere.
it's a 4 outcome measurement
Mhm.
of a 2-level system. When you go to dimension 3, I'm talking about Q trits, and dimension 4 would be Q quarts. So you can formulate quantum mechanics in any finite dimension. In quantum information, usually people are talking about qubits and collections of qubits. So then that would be powers of 2 is the size of the system. But
I see.
But you can have like a 3-level system, a 4-level system, a 29-level system, and like 29, that's a prime number, I think, right? Yeah, so it doesn't factorize. It's sort of just indivisible, a special thing with its 29ness, right, baked in there. And there's a seq POVM in dimension 29. It has 29 squared outcomes. Okay. And you can, which is a crazy thing. And the elements in the vector, if you write it in the computational basis, which is just the normal one you normally write them in, are always very special number theoretic quantities. And this is the obsession of a few people, not me. I don't work on this. The math is too hard. But there's work by Marcus Appleby, Steve Flamia, Gene Kopp, John Yard, a bunch of people like that who have made, Ingemar Bengtsson, have made enormous progress towards trying to prove that in any finite dimension, this structure exists. And I think the latest news is that in a 183-page paper, they have now proved that the question is equivalent to something called the Stark conjectures, which I cannot begin to explain to you. But I think eventually we will know that the structure does exist in every dimension. And then I also think that it is potentially of relevance to, what Cubism at least is trying to say about reality.
Is there anything special about dimension 29 for that?
No. I just mentioned I picked a random dimension.
Mm-hmm.
Yeah.
And so what they're looking for are these discrete structures on like hyperspheres of high dimensional complex space.
Well, it's just in I guess.
Or are they
that's
looking
true.
for discrete structures in the Bloch sphere?
So ultimately,
more points.
No, not in the Bloch sphere. In higher dimensional
Mm-hmm.
complex dimensional space. So I can't visualize it in the Bloch sphere anymore. But say in dimension, for a Q-trit, there's a set of 9 vectors, just vectors that you can write down, which are along these lines. And it's such that if I take the inner product absolute value squared between every pair of them, that is always proportional to, or that is always 1/4. So all of them are equiangular with each other. And essentially due to that, it's a 2 design. So it's sort of a nice drop in for averaging over all of quantum state space in that dimension, at least up to 2nd order in the polynomial. And it furnishes a very nice, for reasons I didn't get into here, representation of quantum theory that I've written about a decent amount in the past. So like, for instance, here, if you use a seq as a reference measurement, then the Born rule can be massaged into a form that looks very much like the law of total probability. In fact, you can prove that it's the closest you can get to the law of total probability that quantum theory admits. Law of total probability being marginalizing over a variable. So I think I probably have it here. Yeah. So this is. Oh, sorry. No, it's not. Okay. No, I don't have it written.
Somewhere where this Born rule is essentially the inference, the Bayesian inference map, a Bayesian map, essentially, because it's an inverse, because its matrix is like an inverse of a stochastic matrix.
I don't usually think about it in terms of an inference, because all of this is sort of synchronic in terms of your beliefs at a current time and detecting inconsistency with them. But in terms of it being like a constraint on what is coherent, so a sort of world coherence, that's usually the way we conceptualize it. But if you want to read about this guy that I was talking about here, then I recommend this paper down here.
By the way, there is like some relationship of seek with mutually unbiased, something like
Yeah,
biased.
exactly. Yeah, mutually unbiased bases. So that's a sort of similar kind of discrete structure. That's actually a collection of bases, and regular like orthogonal bases. But you take several of them, and the inner product or the angle between each basis is the same. And in the dimensions where a complete set of mutual unbiased bases exists, so if you can get a complete set, the maximum number you can get is d plus 1, where d is your Hilbert space dimension. There are some connections between that set and seeks.
Yeah, it's still unknown, right? It's like, oh, maybe.
I think it's known in some dimension. I don't know that it's known in like full generality. It's not really something that I focus on, but definitely explicitly demonstrated in some lower dimensions.
Yeah. Is it like maybe there's something to say about agents and those bases that they do measurement?
Oh, yeah, maybe. I don't know. I should note that while it seems that seeks exist in every dimension, it appears that a complete set of mutually unbiased bases does not. That's not known, but it's very strongly suspected that already in dimension 6, there's no complete set of 7 mutually unbiased bases.
That's very cool. Dugan, any comments in the chat? Any questions?
Memes is asking if there's any connection to 24-dimensional, for instance, with the Leech lattice.
So there is a connection for real equiangular lines, I believe. And there might be a connection for, I think, 1-dimensional less, like in 23-dimensional seek potentially. This is way out of my depth, but a collaborator and friend of mine, Blake Stacy, has written a little bit about sort of exceptional seeks. So indeed, there are, in addition to this number theoretic conjecture that appears to address certain seeks that exist in seemingly all dimensions, dimensions 2, 3, and 8 in particular are definitely special. And that's for similar mathematical reasons that a lot of things end up being special. So like in dimension 8, the reason, unsurprisingly, is quaternions. Or yeah, so that kind of a situation where you have something like a division algebra actually does give rise to a very special kind of seek. In particular, in this case, that seek, called the Hogar seek, is it was one of the first ones found, actually, because it's so nice and symmetric, like even more symmetric than the others. I haven't gotten into any of this at all, but all the seeks that are known are so-called group covariant. So that means that you can start with one element and then apply a group element, a group orbit to it, and that generates all of them. Okay, so with the exception of the Hogar seek, the group that you can always apply is the so-called Val-Heisenberg group, or a discrete version of the Val-Heisenberg group, which is kind of like a discrete version of position and momentum, suggestively. But in the Hogar seek case, the group that we're covariant with respect to is the three qubit Val-Heisenberg group. So it's sort of like inherently 3 copies. But it appears that there's no other exceptions like that. Potentially there's an exception in dimension like 23, which you might guess because of things like the Leech lattice, or 24, but I don't know.
So, and then a similar question would be, what about dimension 8 and the exceptional E8 lattice?
Don't know about E8, but yeah. So this weird 8-ness is coming from I think quaternions or octonions or something like that.
Very cool.
Yeah.
Great. So given all this, what should we potentially set up as a direction for future discussion? What do you think are the big connections here to get us to a middle ground between bottom up and top down?
Yeah. So, well, I mean, I think before we can do that, I personally need to read a little bit more about the Wolfram model so that I could at least come up with a more robust set of, where were we? Not you. A more robust set of the overlaps and non-overlaps. And for each of them, that might, I would guess, suggest some ways forward, or at least things we need to understand more deeply from both perspectives, or see if maybe one perspective doesn't make sense on that topic, or etc. So I need to read a little bit more about that. I hoped that with this, it would be a good primer for some of you to read about cubism. And if we really do want to meet in the middle, we should, see what you guys want to keep from cubism, see what you guys wouldn't want to keep, why not, why yes, what I would like about the Wolfram model, or what other cubists would like about the Wolfram model, what we can't tolerate. Maybe there would be something we can't, I don't know. So yeah, basically try to figure out whether we're really friends, or the degree to which we're friends.
Yeah, and I mean, also just from the perspective of myself, who's been looking at it over the last year in detail, it's more like the Wolfram model is a framework with which you can do physics.
Yeah.
So to the degree that we have a way to explain quantum mechanics, that's just the current framework. That's just the current way that the model makes that obvious. But there's other things that you can do. Ultimately, if it's computational and it's discrete, then it makes sense to us. So that's I think that's
so and it was mostly that aspect that made me think, well, we might not be so different after all. Yeah.
And the other thing that I just want to point out about this top-down, bottom-up approach thing is, like, top-down is bottom-up in reverse. So in some way, if it's very simple and it has this emergent phenomena, it's kind of a bottom-up approach.
I see.
Just taken from the other way around. So we might not be that far away at all.
Yeah, exactly. Like, what you consider to be the bottom, really, it depends.
Yeah, like, are you looking at the results, or are you thinking about it from first principles? I think that's kind of the difference.
Yeah. I mean, I don't think phenomenology would characterize itself necessarily as top down, because they would say, well, actually, we're talking about the basics here, which, the contents of experience. That's what this is all about. So anyway.
Very cool.
Also, I wanted to point out that Spekkens' toy model would also be interesting to look into.
Oh yeah, for sure. You guys,
a minimal,
you need to read that paper.
Computational model for.
I think I've read it already. It's basically like it's all about, like, this traditionally regarded, problematic phenomena. It's basically, they say it's like there's a toy model for every quantum phenomena, but non-locality, essentially. That's all the inequalities are the only problematic things. So as long as you have, like, a constructive way to explain that, you're golden, right? And by the way, speaking of, like, the reverse, and I was also going to ask you about the relation. Do you know, like, the original Feynman-Wheeler absorber theory about, like, particles going backwards in time? And I was wondering whether you have, like, any ideas of this, of the relationship of this with the inference itself, because it's kind of something going backwards.
Yeah, I really don't have anything intelligent to say about that, except to note that there is some recent work. It's maybe not all recent, but anyway, there is work on what people call Bayesian retrodiction, and that's been extended to quantum Bayesian retrodiction. I don't know that it would. I don't think it will involve, like, proper backwards in time, like maybe what you actually have in mind, but at the very least, it's about talking about the past. So possibly something to look into.
Yeah, definitely sounds interesting.
Yeah. Like dynamics. Otherwise, I don't
Yeah.
see any like possible ways to derive dynamics of this interdiction without actual time reversal or any
I
kind
see.
of thing.
Yeah. So I would recommend you all read the Spekkens paper just because it's a good orientation for a broadly epistemic point of view. And like my impression of what's been written regarding quantum mechanics for the Wolfram model is it's way more ontic. Like it looks a lot like many worlds. You're just saying, okay, now we have branching computation, whatever. Like my attitude would be that that's a false flag. Ultimately, the quantum effects are going to be at a higher level. At least from a qubits perspective, that's what we would expect. So maybe that's
I think it depends on how you define the agent, or
Yeah.
in our case, maybe the observer. If you define the observer as something almost primary, then it can be emergent from a foundational perspective. And then sometimes the way I like to think about it is you have like a collective observer, which is how we experience the world as like larger, more hierarchical things. But it doesn't mean that at the foundations, observer can't be a very, very discrete, finite thing.
Yeah, exactly. And that's another, I mean, that's exactly where I'm trying to, or that's where I want to try to break the cubism idea apart into a simpler kind of agent. At least understand sort of how that's controlled, because at present we have completely unrealistic, essentially ideal Bayesian decision makers. And if we make that weaker, then you don't get exactly the full quantum mechanics, presumably, but you should get something that has some quantum features. And like if I zoom back to like the simplest thing, maybe I would want to call an agent, what's like the simplest, what is actually left of what sort of feels like quantum mechanics at that level. So like you sort of have to treat them hand in hand. They're co-emergent kinds of things. It would be my intuition, but I've made no progress on this. Although my impression is that potentially the Wolfram model could be helpful for this, because you might be able to bake into it sort of things like agents at sort of different levels of complexity.
Yeah.
But the problem
At least that's a wish.
The problem is like not how to construct the agent, but more like agent's belief, how to actually encode his beliefs and probabilities into the system. Because it's not very natural to like embed the numbers, like an actual like histogram of the beliefs into the system. It's not very natural. So you have to somehow overcome this problem first.
Okay, I agree. Yeah, that's so then again, the full description of like the way I talked about it would have to be sort of an abstract description, but then what we actually like on the computer simulate or whatever would not actually have a full state like in a register somewhere or anything like that. Maybe, I don't know.
Depends on the algorithm. Like you can make the algorithm more complicated or the state more complicated. At some point, if the algorithm is complicated enough, it could encode any possibility in the state. And the state doesn't have to be that large at all. But yeah, I think we should maybe for the next engagement have like more of a live science interaction, and let's think through some ideas and actually explore some of the directions. Because I think there's definitely some interesting things that more like of a discussion style thing that we can just explore.
Yeah, sounds good.
Sounds good. Okay, great, John. Thanks so much for that. I really appreciate it. That was a great presentation and a lot of work to investigate here.
Yeah, so we all need to go read. Let's do it.
Okay. All right, until next time.
See you guys.
Yeah.